on higher rank abelian and discrete symmetries.
So I'd like to thank the organizers to invite me to a math conference, actually being a physicist. The topic I chose is the subject I've been pursuing over the past few years, which involves the study of both abelian know how to point. And I have nowhere to stand unless I want to fall off the. Yeah, but this no. Okay, it's very weak, right? You see, I don't. Okay,
Maybe
I
one you
can
come here. I'm good. That's so good.
Okay. All right. So the topic is abelian and discrete symmetries in F-theory compactifications. Those topics are actually closely related to Ron's numerous contributions, the interface with physics, including a few years ago, mini revolution in F-theory compactification that he was a leading contributor to. As a colleague at Penn, he is very generous and patient talking to us physicists, including myself, and teaching us about different aspects of algebraic geometry. Actually, this patience led to some of the collaborations I had with him, in particular a paper on heterotic string theory and a few papers on F-theory compactification, including one of the topics I'm going to talk in this lecture. So I wish you really a very happy 60th birthday, also with the hopes that we'll continue our collaborations. So the outline of this talk is to try to give you some physicist motivation for F-theory, in particular to address aspects of particle physics that is encoded in geometry of singular elliptically fiber Calabi-Yau manifolds. I'll highlight few building blocks in those constructions, in particular how we obtain non-abelian gate symmetry, massless matter and their representations, as well as possible Yukawa couplings among these matter representations. Among particle physics models, of course, I'm going to highlight my own, which is a recent example of the globally consistent, actually first globally consistent three-family standard model directly. But the main topic in the second part would be to highlight some formal developments in studying F-theory compactification, in particular constructing a global elliptically fiber Calabi-Yau manifolds that possess abelian gate symmetries. Those constructions are related to elliptically fiber Calabi-Yaus that have additional rational sections that are also closely related to a Mordell-Weil group of rational sections on elliptic curves. The last part will be devoted to studying discrete symmetries in F-theory compactifications, and that would result in studying genus 1 fibrations, namely fibrations without sections, but they have multi-sections, and highlighting connection of these geometries to Tate-Shafarevich group in this context. Well, I'm going to mainly overview topics, and I apologize, it's going to be UPenn-centric. Namely, I'm going to talk primarily on things I've been working on. So, in particular, on aspects of F-theory compactifications with abelian gate symmetries that led to constructions of higher rank abelian gate symmetries associated with higher rank Mordell-Weil groups, both rank 2 and rank 3 Mordell-Weil group constructions, which correspondingly lead to U1 square gate symmetries or U1 cube gate symmetries. What I'm going to highlight in this context is primarily work with rank 2 constructions. I should point out that this work was done in collaboration with a number of junior people in our group. Dennis Clevers, former postdoc at Penn, now fellow at CERN. 2 students, Hernan Piragua and Peng Song, as well as another mathematician at Penn, Antonella Grassi. And most recent work also involves the work with Waddy Taylor. On another side, when I turn to F-theory compactification with discrete symmetries, namely not elliptic fibration, actually genus 1 fibration with n sections, and its relation to Tate-Shafarevich group, I'll highlight again higher rank construction associated with Z3 symmetry, rank 3 discrete symmetry, and this is recent work together with Ron, as well as a new postdoc at Penn, Maximilian Korychkin. So in terms of highlights, as I said, I'm going to on the abelian gate symmetry side, I'm going to highlight just a few points about rank 2 constructions first, particular specific constructions of rank 2, and then generalizing those constructions that allow us also to move rational sections in a moduli space and study abelian enhancements of those non-abelian enhancements of those abelian gate symmetries in the context of Mordell-Weil rank 2 construction. So this side. So analogously, those two things would turn out to be related, both rank 2 Mordell-Weil constructions and rank 3 Tate-Shafarevich constructions will turn out to be related through what we call conifold transitions that I'm also hopefully be able to highlight to you. And as motivation for particle physics, I'm also going to highlight the example of 3 family models that contains U1 gate symmetry, and that was actually more recent work together with a number of students at Bonn University. Okay, so with this introduction, let's go ahead and try to motivate F-theory per se, which typically we try to describe as non-perturbative regime of what we call type 2B string theory, where the so-called brane constructions that in perturbative context of string theory are boundaries of open strings become non-perturbative and thus turn into geometric description on compactified spaces, which are not Calabi-Yau anymore in the base. But in addition to this fully back-reactive description in terms of geometry of the branes, that's describing strongly coupled regime, we add to the construction also the parametrization of the string coupling as part of the toroidal geometry that we fiber over original compactification. So F-theory is basically describing now geometries where we are taking string coupling as part of the toroidal torus fibration over back-reacted now non-Calabi-Yau space. And it's effectively describing a theory in 12 dimensions. But really the focus is really now on the geometry. So it's really, the core is studying elliptically fiber Calabi-Yau manifolds, starting with 12 dimensions and thus describing now the theory in compactifying on one complex dimension higher space, namely Calabi-Yau fourfold, if we want to describe four-dimensional solutions. We often relate this description by dualities, a circle reduction that would lead to effective description, what we call M-theory or 11-dimensional supergravity, and that will be primarily the only duality that I'm going to build, that I'm going to use in my studies beyond the actual geometry of elliptically fibered Calabi-Yau spaces of F-theory. Of course, as physicists, we like lots of other dualities, including the heterotic duality, which I'd love to talk about based on some recent work with Anthony Lagrassi, but I'll skip that for this topic today. All right, so since I motivated F-theory as non-perturbative regime of string theory description, this naturally is intriguing for physicists because we would have a way of getting information about a regime of string theory that is non-perturbative and trying to derive particle physics in this non-perturbative regime. One of the main motivations for the recent mini revolution in F-theory compactification had to do with the fact that in this non-perturbative regime of string theory, certain couplings, for example, in grand unified models that were absent in perturbative description are now there directly in this non-perturbative regime, in particular, certain coupling of meta representation in the so-called SU5 models. Also in this non-perturbative regime of string theory, the exceptional symmetries naturally appear, both at the level of genuine gate symmetry as well as the global symmetry associated with the representations or couplings in the theory. And so it's intriguing to study this regime where geometrically we naturally see appearance of exceptional gate symmetries. By the way, in perturbative domain of type 2 string theory, this is not possible again. So just with those basic motivations, right, we turn now to address this particle physics phenomena by describing, learning more about the geometry, which is now described in terms of elliptically fibered Calabi-Yau spaces, but they are singular because the back reaction of D-branes that becomes part of the geometry is really encoded in those geometries as singularities. So learning and studying such specific spacetimes will allow us to determine some key, what we refer to in particle physics, discrete set of data. Namely, we could derive in these compactifications the gauge symmetry, the matter, in particular their representation under the gauge symmetries, as well as their multiplicity, as well as the existence of couplings among these matter fields. As far as what we refer to as continuous data, we are not, those are much harder questions, in particular the actual magnitude of couplings. Calculable techniques along those directions are really at very early stages. So my focus will be really primarily on the first two discrete data aspects, gauge symmetries and matter representations along with their multiplicities. All right, so again, going back to basic ingredients to describe F-theory, as I was alluding to, we are now in a regime of strongly coupled type 2B theory, where the string coupling along with the corresponding Ramond form, namely axiodilaton, which are fields parameterizing the strength of string interaction, become part of the geometry. So they are effectively axiodilaton combination becomes a modular parameter of a 2 torus, thus signifying the manifest SL to Z symmetry which is a non-perturbative symmetry of type 2B theory. So this 2 torus, whose modular parameter signifies the strength of a string coupling, is fibered over now the original compactified base that is now non-Calabi-Yau. So in this fibration, in particular, the simplest, the prototype way of describing this fibration is via Weierstrass form. And as we study the fibration over the base, we see in these cases that at the loci in the base, where the fibration degenerates, we end up typically with singularities of certain codimensions, and the nature of the singularities signifies the appearance of the original back-reacted non-perturbative branes. So the key thing is to really study the total space of torus fibration for singular elliptically fiber Calabi-Yau manifolds, which should be fourfolds if we want to study the theory in 4 dimensions, from 12 down to 4, and it has to be Calabi-Yau in order to preserve the minimal amount of supersymmetry in effective 4-dimensional theory. For a lot of geometrical purposes, we often like to study also compactification on singular elliptically fibered 3-folds, which would allow us to study effective theory in 6 dimensions with n equal 1 supersymmetry. So again, the nature of the singularity is in the Calabi-Yau, in this elliptically fiber Calabi-Yau spaces, encodes basically the involved setup of original intersecting deep branes that in the perturbative regime corresponding to the base to specific boundaries of open strings, all embedded with the base being corresponding three-dimensional non-singular Calabi-Yau space. Now in this case we are just dealing with the geometry. The base is full of singularities. In particular, at codimension 1 singularities, we observe ADE type singularities associated basic with the divisors that were wrapped by branes in the original geometry. When 2 divisors intersect in the base, we are dealing with codimension 2 singularities, and at this intersection, this signifies the appearance of matter. In particular, if we want to study in 4 dimensions what we refer to not vector-like matter, but chiral matter, we have to add something in addition to geometry, namely from borrowing from M-theory duality, we have to add a specific flux for foreign field strength flux that would induce when added to this intersecting curve where matter appears, it would basically render the matter, nature of the matter chiral, more left-handed than right-handed particles, which is, of course, the property of the standard model. And at the triple intersection of those divisors, this is codimension 3 singularity, this would signify the appearance of coupling. So if we see that geometrically, this would signify that such a coupling is possible, but we cannot determine the magnitude with current techniques. So to turn back to the well-known story of appearance of non-Abelian gate symmetries, well understood by Kodaira and a number of other people in mid-late 90s, has to do with the appearance, as I was mentioning, of codimension 1 singularity, where along the divisor, the fibration becomes singular. Now the nature of this singularity is parameterized basically by the order of singularities of F and G, as well as the discriminant of the Weierstrass form. And so this order of singularities is in 1-to-1 correspondence with the singularity type of this codimension one singularity. So the way we turn to study the nature of the singularity type, we go to resolution, and in the resolve phase, we replace resolved phase produces for us basically a structure of a bunch of spheres over this divisor S, and the structure of the sphere, for example, IN singularity, is in one-to-one correspondence with what we call SUN Dinkin diagram that signifies the corresponding gauge symmetry. So the way this connection to gauge symmetry works is we interpret the massless gauge bosons in lower dimensions. Okay. Actually, now going to M theory description, a Kaluza-Klein reduced three-form gauge potentials along the 1,1 forum in the resolved elliptically fiber manifold. It turns out that the number of 1,1 forums is in one-to-one correspondence of the resolved P1 spheres that signify the nature of this resolved resolution. And so, in particular, all the Cartan generators of non-abelian gauge symmetries are directly related to a number of spheres in the resolved resolution. Now, the way we get non-abelian gauge bosons corresponding to non-abelian part of the gauge symmetry, they would be associated in the M theory language by looking at M2 branes, namely non-perturbative effects in M theory that wrap those cycles in this, and the nature of the structure of those spheres is in one-to-one correspondence again with the nature of the non-abelian generators of the gauge symmetries. And it's those guys together that produce for us in 4 dimensions massless spin 1 particles with the gauge, a non-abelian gauge symmetry associated with the corresponding Dinkin diagrams that are in one-to-one correspondence with the result singularity. Anyway, this would be the nature of gauge bosons, non-abelian gauge symmetries, but in these constructions, of course, we also get massless matter. And this massless matter appears when 2 divisors intersect at the base. So at this codimension 2 singularity, of course, the fiber also degenerates, and the resolution of the singular fiber generically produces in codimension 2 I2 fiber. So 2 P1s attached together, and the way we identify existence of matter, again from M theory picture, we wrap isolated M2 matter curves coming from M2 branes that wrap particular P1 in this I2 fiber, and the charged matter, namely the actual charge representation of that matter, is determined by using the intersection theory in this resolve phase associated with this resolved I2 fiber. So we have both techniques to determine at the level, technically at the level of codimension 1 singularities and codimension 2 singularities, both the appearance of non-abelian gauge bosons, non-abelian gauge symmetry, as well as the actual representation of the matter that appears at the intersections of this divisors that support non-abelian gauge symmetry. And we actually can calculate both, not just the charges by using the intersection theory of the matter, but also the multiplicity of this matter, which is another way of determining how many copies of the matter we have. Now, with these key ingredients, the initial focus in the study of F-theory compactification was primarily on SU5 prime unified theories, claiming that they are natural frameworks in which the right couplings could really exist directly in F-theory that were absent in perturbative type 2 theory. So that led, as I mentioned a number of times, first to early local constructions, namely elliptic fibration was not really globally defined directly, but was just studied the appearance of SU5 gate symmetries, and the matter was really done locally only in the resolution. But later on the techniques have improved, and one ended up with consistent global constructions, including the ones by the people here, Tony and Herb, and he actually talked about some further progress. So there's actually a full talk at this conference that highlights some of the aspects of studying of global grand unified models and appearance of matter that is desirable for particle physics. Now, briefly, let me just mention that I want to actually plug in also constructions of other direct particle physics models, namely not starting just with grand unified models, but having directly standard model building blocks that can be done in specific cases that would lead to globally consistent three-family standard model, but also other possible particle physics groups like Padi-Salam or trinification models. So very briefly, let me highlight these constructions that led to the three-family standard model directly. It was used by, obtained by using core Toric geometry techniques, where actually torus fibration was constructed as an elliptic curve in elliptic curve as a genus 1 Calabi, no, genus, one-dimensional Calabi-Yau space constructed as hypersurface in specific two-dimensional toric varieties, namely those associated with the so-called 16 reflexive polytopes. So elliptic curve is basically a hypersurface constraint, in particular two-dimensional toric variety, and actually is described as anti-canonical divisor in this toric variety. So those are just 16 possibilities that we can in principle now elliptically fiber over a chosen base, promote both the coordinates of these two-dimensional toric varieties as well as coefficients of the hypersurface constraint. We promote them to lift to sections of line bundles that have to be of certain degrees in order to ensure Calabi-Yau condition. It turns out that for these examples of hypersurfaces in two-dimensional toric varieties, the whole fibration is determined only by two divisors in the base. And for each of these examples of elliptic fibrations, we can construct corresponding model, basically whose features are encoded only in this fibration, and in particular, the so-called polytope F11 produces the standard model gate symmetries for us. In particular, this is now hypersurface constraint in DP4. So that would be the associated with F11 polytope. And so this elliptic curve is now promoted to elliptic fibration over the base, and studying codimension 1 singularities as well, the one associated with U1, produces for us generically in this context SU3 cross SU2 cross U1 gate symmetry. And at the level of codimension 2 singularities, we can also determine the corresponding representations, okay, that fit precisely into the multiplet of quarks and leptons of the standard model. Okay. Now, this is not enough, because we need also to determine the number of these chiral multiplets. Namely, we cannot make them as vector pairs because nature makes 3 copies of quarks and leptons and no right-handed conjugate in nature. And so for that purpose, we have to go to a more technical thing by adding also the 4-form flux field strength that has to be integrated over the meta surface which is basically this meta curve fiber over the curve at the intersection of two divisors. And so both the flux has to be of special form because we don't want it to give us the superpotential per se, so we really want it to contribute only to the chirality of matter, and so it has to sit in the middle vertical cohomology of this resolved Calabi-Yau space. And we have to also geometrically determine the matter surfaces in this context, which can be done, again, by techniques of algebraic geometry, by the so-called resultant techniques. And that calculation can be now specifically done for these examples, but that's not all, because Ehrlich flux forces us to introduce new consistency constraints, the so-called tactile cancellations, because the flux sources another type of configurations. And so we have to satisfy what we call the Gauss law on this compact space due to introduction of 4 flux that has to be satisfied through this equation. This is the left-hand side is Euler number of the resolved Calabi-Yau, and this is contribution from the fluxes. And we have to add now the sources with the associated with the so-called D3 branes. And this is highly non-trivial condition that has to be satisfied for positive integer number of D3 branes. And in retrospect, we also check consistency by checking quantum field theory that all our anomalies are cancelled. So we've done that. And surprisingly enough, we can get consistent models. Now we're turning on these fluxes that have standard model gauge symmetry and the right representation of matter and chirality of matter. And we could get the standard models just with the simplest possible choice of the base, like P3. The whole elliptic fibration depends only on 2 divisors I was referring to, which in this case are just multiples of the hyperplane divisors of P3, with coefficients, number integers n7 and n9 being allowed only in certain range of integers in order to maintain Calabi-Yau conditions. Okay? And then we check whether we can satisfy tactile conditions for different choices of fluxes and study what kind of models we have. And indeed we have models that have chirality number of families that is non-zero, and they are consistent for the positive integer value of a number of branes. So the key thing is to see that we actually, even in the simplest choice of base, get examples with 3 families of quarks and leptos, chirality 3, and positive integer number of D3 branes. So it's sort of an interesting thing that one can directly do this construction. That is, my string phenomenology side. And now in the last part, which is about probably, 20 minutes, 40 minutes? No, 20 minutes, 20?
We got more than 20 minutes.
20 minutes, okay. Now I'll go to the more formal aspects and highlight some of the developments there. Okay, so turning now to the second part of my talk, I'll turn now to the studies of abelian gauge symmetries in F-theory. And again, I already had an example, which is standard models. So abelian gauge symmetries are clearly needed in direct construction, say, of the standard models, as well as in constructions of models beyond the standard models. Sometimes we need additional U1 symmetries to prevent certain couplings for certain different phenomenological reasons. So actually multiple U1s are quite desirable in this construction. Okay? Now, as far as geometry goes of elliptically fibered Calabi-Yaus, it's a new type of geometry because namely those are fibrations with additional rational sections. And it was quite surprising until a few years ago that while non-abelian gauge symmetries are understood now for a number of years, at least conceptually and also in practice, abelian sector was rather unexplored and was really revived only in the context of applications to particle physics in the past 3-4 years. So the key thing is for abelian gauge symmetry is that to get just a U1 gauge boson, from M-theory perspective, we have to expand the three-form potential just in terms of a single one form on the result on the Calabi-Yau space, and we should forbid any kind of M2 branes wrapping different P1s. This means that actually this 1,1 form can only be associated with I1 fiber. Okay, that means no singularity. Okay, and it turns out, again, this was one-known fact from way over 20 years ago, that the existence of such single 1,1 form is in one-to-one correspondence with existence of rational section on the elliptic vibration. Now, rational sections of elliptic vibrations, of course, we start with rational points of elliptic curves, and there, such rational points of elliptic curves that are solutions in the Weierstrass form of that equation turn out to form a group under addition, the so-called Mordell-Weil group. So if we, in addition to zero section that we have for elliptic vibration, find additional rational points on the elliptic curve, these points form a Mordell-Weil group under addition. Now, in vibration, we have this rational points is promoted to rational section, okay, of elliptic vibration, and basically in the full vibration, this section organizes things in such a way that there is automatically guaranteed a second copy of the base, okay, so because of this bookkeeping of rational section, okay, keeping a clear bookkeeping of a map from the base to the points on a torus, provides us with a way of finding directly additional new divisor, the so-called non-local horizontal divisor. Okay? And from this non-local horizontal divisor, we can construct via Schroeder map directly the corresponding 1,1 form that now supports the U1 gauge boson of four-dimensional theory. So these rational sections are in one-to-one correspondence with 1,1 corresponding one forms that support massless U1 gauge bosons. So arguing this way, what we have to do is to get non-Abelian gauge symmetries, namely we have to construct these non-local horizontal divisors by finding additional rational sections in the elliptic vibrations. Now, lucky for me, I understand that Dave Morrison was discussing some of these topics, how one can in principle systematically find a number of rational points on elliptic curve, in addition, of course, to the 0 point. Okay? And the core thing is that realization that with n rational points and 0 points on elliptic curves are associated with the line bundle of degree n+1. Okay. And it's the sections, natural number of sections of this line bundle is n+1. Okay. Now, if we are dealing with higher powers of the line bundles, we would get additional number of sections. But in the case of n equals 0, namely only 0 section or 1 section, this would introduce new sections. It's only once we go beyond n equal 1, namely Mordell-Weil n equal 2 or higher, the relations among, as we go to higher power, there is actual relation between those sections. So due to these additional relations, the natural way of constructing now elliptic curve with n additional sections, namely n bigger than 1, would be typically embeddable as a constraint in weighted projective space. So as I'll turn to rank 2, we'll see concrete example, but typically the construction of elliptic curves with and additional rational section will result in a non-generic Calabi-Yau one-fold in such a weighted projective space. Now, in special constructions, we can also view constructions as generic Calabi-Yau, but in a blow-up of the weighted projective space. In this case, it's more general one Calabi-Yau, but in the blow-up of the weighted projective space where rational points are associated with the blow-ups. So those are things more said in words. The concrete constructions actually were revived not too long ago by Morrison and Park for constructions with n=1, so one additional rational points that was constructed as generic Calabi-Yau now in a blow-up of P112, so weighted projective space with blow-up at one point. Okay. Our contribution of our group was actually constructing rational sections, 2 additional rational sections, okay, Mordell-Weil n=2, which was originally a generic Calabi-Yau one-fold in dp2, so this is p2 blown up at 2 points. More recently, we generalized those constructions now as non-generic cubic construction now in P2 itself, which I'm going to hopefully turn to shortly. In this program to construct elliptic fibrations with more and more rational sections, one actually is encountering a difficulty. In particular, for n=3, our group managed to construct examples as complete Calabi-Yau intersection as a blow-up of complete Calabi-Yau intersection in blow-up of P3 in 3 points. Now, as one goes to higher examples, n=4, it turns out that those are overdetermined systems, and it's not clear how to concretely, explicitly construct that. Those are the so-called detrimental varieties, and we didn't manage to really make sure that we are dealing with really as general constructions as we would want to. So this is the program is sort of now at a stalemate. But let me highlight this concrete example that I was referring to that has Mordell-Weil rank 2, and it's a generic Calabi-Yau space. One-fold described as the specific, most general hypersurface in dp2. And the appearance, as I was referring to already, the appearance of the corresponding zero section and the rational, additional 2 rational sections is represented by intersections of different divisors in dp2 with this constraint. We actually, for these constructions of a generic Calabi-Yau one-fold in dp2, we managed to get also the general charges of meta representation as well as their multiplicity. So basically constructing that just from the features of fibration and representing multiplicity just in terms of intersections of corresponding divisors in the base. Now, more recent development from the summer is actually building on more general, beyond this construction, namely allowing to the rational points to move more freely. And that led us now to construction that is non-generic cubic construction. So it's a non-generic one-fold in P2 constructed as a non-generic constraint, cubic constraint in P2. Now, writing it in this particular way allows us to change the complex structure parameters AI and BI in such a way that we can move this rational points in a curve and actually collide them together. And what we expect is, as we collide those sections together, we could in principle study non-moduli space non-Abelian enhancement, okay, as those points collide. Okay. In particular, these non-local horizontal divisors associated with the rational points that signify abelian gate symmetry turn now into local vertical divisors that signify Cartan generators of non-Abelian gate symmetry. And we actually can study in more general context how this, in the modular space of this U1 square construction, we get at particular locations in modular space enhancements to non-Abelian gate symmetry. And we demonstrated that both in geometry by doing global resolutions as we reach, as points collided and once the non-Abelian gate symmetry appears, and also determining fully the massless spectrum that in turn allows us in field theory to do phenomenon of giving vacuum expectation value to these fields and breaking non-Abelian gate symmetries back to Abelian ones. So we understood, at least in this context, we understood that quite well. The point in this context is that this is much harder than studying just U1, single U1, because we have much richer structure. In particular, as we collide those points, we observe the enhancements to SU3, to SU2 cross U2. Those are enhancements as points, as we create vertical horizons, vertical divisors that produce non-Abelian gate symmetries that preserve the rank. But in general, we can also have examples where the rank is not preserved. It's really much higher gate symmetry that can appear, as we have in general these collisions of rational points that we actually rigorously study. And as a byproduct, intriguingly enough, we needed for this phenomenon in the field theory context the existence of particular matter representation, okay, that would then break such symmetries down to U1s in this context, and it's associated with first explicit construction of symmetric representation of SU3, which is geometrically not trivial construction of matter appearing codimension to singularity. So just as a technical advance. All right, so I have 10 more minutes, at least 15 minutes. Okay, which brings me to the topic, right, when I can highlight some of the things that we understood by collaborating with Ron, which is the study of discrete symmetries in F theory. Okay. Any questions? All right. So again, physics motivation is obvious because we typically, again, in constructions or beyond the standard model physics, do need discrete symmetries because standard model a priori at the level of couplings does not prevent coupling that would produce proton decay or other very exotic processes that we don't see in nature. This is associated with the so-called parity violating terms. Okay? And discrete symmetry would play a natural role in the standard model. If we have to, in addition to the standard model, also specific discrete symmetry, we could prevent bad couplings about matter that could produce, say, proton decay. Okay? So it's desirable to have constructions with discrete symmetries. And also, you know, at the end, we want to use often such discrete symmetry to address the hierarchy of couplings about matter fields. Okay, so this is referred to as family texture. So this is, for particle phenomenology, this is clearly desirable. And so to know how to construct F-theory compactifications that have discrete symmetries is a desirable feature. Okay? Now from the geometry point of view, it's also intriguing because those are not elliptic fibrations anymore, but the construction is based on genus 1 fibrations that, of course, do not admit a section, but a multi-section. And there was some earlier work in the late 90s, but again, this is just 2-3 years old effort when we are motivated by particle physics and trying to understand the nature of discrete symmetry in F-theory compactification. Now, since I spent all this time describing the constructions with abelian gate symmetries, there is actually a natural connection in moduli space between constructions that have abelian gate symmetries and those that have discrete gate symmetries. Okay. And they are related basically by doing at certain codimension 2 singularity loci deformations from constructions with abelian gate symmetry into new geometries that have only n sections. And these deformations in physics community goes under the language of conifold transitions. So there is actually a transition between constructions with abelian gate symmetries that would lead into constructions with discrete symmetry. So more specifically, let me just talk about Mordell-Weil rank 2. No, sorry, this is not Mordell-Weil. This is Mordell-Weil rank 1. That means 0 section and 1 additional section. So we have a construction, say, with U1 gate symmetry with 0 section and 1 additional rational section. Okay? Now we have the elliptic fibration over the base, and generically it happens that elliptic fibration degenerates at the codimension 2 loci in the base. Okay. We know that at codimension 2 loci in the base we would get the matter. But just now as the geometry, we get an example of codimension 1 singularity, okay, where those sections collapse. Okay? Now we can, typically what do we do in this construction? We resolve the singularities and talk about the resolved construction and determine the matter at this point associated with this abelian gauge constructions. Okay? But we can go another way. We can actually deform this codimension to singularity via deformations associated with what we call in physics conifold transition, deformations that would turn this collapsed, okay, codimension 2 singularity, okay, into a regular construction, but now there are no sections anymore. These collapsed sections after deformation become basically a single bisection. Right? So we have this geometric picture where at codimension 2 loci we see that, you know, there is a blowdown of 1p1, okay, where those sections collapse. Now we glue inside, we glue here 3 spheres that now make the geometry regular, but the original sections become part of a multi-section. Okay? So this is a geometrical picture of how we believe this connection goes from constructions with U1 symmetry to constructions that have only bisections, say in this particular example. Right? We also see in field theory what is happening, because at this singularity there is appearance of matter. Say there is a matter that has a charge 2 under this U1 abelian gate symmetry in the original construction. Okay. This matter can get a vacuum expectation value, can be Higgsed. And Higgsing this matter with charge 2 produces for me the vacuum that has Z2 leftover gate symmetry. Had it had only charge 1, it would go to nothing. But in this particular case, there's the precise matter with charge 2 that appears at this construction, that in field theory we view that as Higgsing this field and producing now this geometry associated with, after Higgsing, just with the gate symmetry that is Z2. Okay. So we have this picture where we know a lot about the first part. We've done a lot of constructions with abelian gate symmetry. We have studied the actual codimension 1 and 2, in particular codimension 2 singularity, and get the matter in the context with the abelian gate symmetry. So we know a lot about the geometry where we are dealing with rational sections, both gate symmetry and the matter. Now in this context, it's very hard for us to calculate directly matter when we have discrete symmetry. So there in this deformation phase, we use field theory that we obtain by constructing magic fields from the geometry. So this is a typical approach in this context over the last 2 years, where actually we focus on the geometry and the spectrum in the case when we have sections with abelian gauge symmetries, and then from effective theory determine what are implications for the phase with the discrete symmetry after fixing. Okay? And that was done specifically for Z2 in this context, and our work focused on a higher rank, which is Z3. In particular, the Z3 study is now associated by finding a direct construction that has U1 gauge symmetry, but the charge matter 3. So this is non-generic matter 3, whose Higgsing would produce for us after breaking U1 down to Z3 symmetry. Now I have 2 minutes where I would also like to highlight what is the role of what we call Tate-Shafarevich group and the constructions of these geometries that have n sections. And my focus, as I said, is on Z3 symmetry, and is going to be associated with the geometry that has only 3 sections. So as Ron taught us, the key feature of Tate-Shafarevich group is that it's based on a collection of geometries, elliptically fiber Calabi-Yau manifolds that have multi-sections. So it's a collection of genus 1 fiber Calabi-Yau manifolds, but they all have the same Jacobian fibration. So for whatever geometry we have with n sections, they all have to end up with the same Jacobian fibration. Now, elements of Tate-Shafarevich group don't have only to do with these geometries. It also have to do with the actions of Jacobians on these geometries. So each element of Tate-Shafarevich group consists actually of a triple, okay? Namely, the genus 1 geometry fibration over a base. The second element is the fibration map. And the third one is really the Jacobian action on this multi-section geometry. So each element of Tate-Shafarevich is specified by all these 3, by the whole triple of that type. Okay? So it can turn out that we have the same geometry, but there could be inequivalent actions of the Jacobian on this geometry that would produce now different elements of the Tate-Shafarevich group. Okay? That's something that we were hung up for a long time, including other physicists, that actually you can have just one geometry but different actions of the Jacobian on this geometry, which produces for you more elements of Tate-Shafarevich group. So for Z3, this specifically means that we have really only one geometry with a trisection, but now Jacobian action can act in one direction or in the inverse direction on this particular 3-section geometry. So the elements of Tate-Shafarevich group actually are associated now, while we have only Jacobian and a single trisection geometry, we actually have in Tate-Shafarevich group 3 different elements. Okay, because the Jacobian action and its inverse produces for us different elements of Tate-Shafarevich group. So one would want to ask oneself, what's the relevance of the Z3 symmetry? Because actually, for F theory, it doesn't matter much. Okay? For F theory, what I was referring to, we can start, and I'm going to now go for concreteness, just go to 6 dimensions. So I'm compactifying elliptically fiber 3-fold, not 4-fold. But we start with the 6-dimensional F theory that has U1 gauge symmetry. If we can construct charge 3 field in this geometry with a trisection, say, no, sorry, this is not this is the elliptic fibration. So we have elliptic fibration with U1 gauge symmetry, okay, and non-trivial matter appearing with charge 3. So Hicksing this matter we know will produce for us Z3 symmetry, which is F theory either on a manifold with trisection or is Jacobian. F theory doesn't care. So actually, what is the role of Tate-Shafarevich group if F theory really doesn't care in this phase, you know, whether it's compactified on a trisection manifold or on its Jacobian fibration? Okay? The difference and the role of Tate-Shafarevich group really appears in the duality between F theory and M theory. And this is very much physics language, and I really don't have much time. People would like to go for dinner. So let me just highlight that there is a key feature now that the role of Tate-Shafarevich group really plays an important role in M theory, where we actually start with the 6-dimensional F theory, compactifying on circle, and produce now in 1 dimension lower the M theory that has now 2 U1 symmetries. One inherited from the original example, but now the Kaluza-Klein U1 that typically comes in this reduction. Now, because of the discrete symmetry nature, we can actually turn on this cycle, on this circle, a background field, the so-called Wilson line, okay, that produces for us a changed Kaluza-Klein spectrum after reduction, whether if we turn on this, this background Wilson line. Namely, the Kaluza-Klein spectrum now decomposes into fields whose matter mass depends on the value of the background field at the level of the Kaluza-Klein field. So one sees that actually, depending what you choose for this background field, you can get massless fields in 5 dimensions, charged under both U1s, okay, that would have different charges. So if there is no background field on the circle, then we have back the same charge, 3 under U1 and 0 under Kaluza-Klein. But if we turn this quantized background flux, which has to be quantized mod 3 to get integer level states, the massless states there would have different charges. Okay, -1, 2, and 2, 1. Now in the M theory language, depending what we chose for the background fields, we get different type of charge massless fields, 3 of them. If the first one Hickses it with charge 3, 0, what we have is M theory with U1, Kaluza-Klein, times Z3, the inherited Z3. Okay? If this guy with the background fixed flux is Hicksed, that will produce for me now the single U1 symmetry. But there's the third one too that we found, and this one also produces another vacuum in F theory. So in M theory, in the discrete phase, we get 3 vacua. Okay, one with the U1 cross Z3, okay, and the 2 additional ones. And it's those 3 vacua that are in 1-to-1 correspondence with the elements of Tate-Shafarevich group. Okay. So actually, I don't have the time, but we've done more physicist work with Ron's help. We actually identified the existence of all these 3 matter fields. In each phase of blow up of the geometry that we deal with the U1 field and the charge, 3 in 6 dimensions, then we identify in different phases either 3 -1, 2, and 2 -1 massless field in M theory, and deduced this one by studying Gromov-Witten invariant, and found this one indirectly. Or we went to a new phase, which was flop resolve phase, and we found 3-0 guy directly. Okay? So the upshot is that we actually verified also directly by calculating the massless matter for different phases in M theory, the right matter that does the work. So since I don't have time, I don't want to bother you too much with this, but just highlight the outcome. That what we've learned by studying higher rank discrete symmetry is that as far as M theory goes, we have to do non-trivial work to find all the 3 massless fields that do the Hicksing in M theory, namely Two we get in one phase, by the third one we have to do the diagram of with an invariant calculation. Or we go to the flop phase and find the 2 and 1, the missing one that was here obtained just indirectly by studying the curves associated with Gromov-Witten invariance. But we basically demonstrated the really non-trivial connection between the role of Tate-Shafarevich group in M theory and identifying all the right correct matter fields that do the Higgsing now in M theory language. So I'm done. Okay. So I should thank you all by going through. I'm not finishing yet, but I should thank you to listening to physicists telling you about things that you know much better, but really having in mind applications to it. And so you'll see I spent quite some time arguing about building blocks of F theory, but also showing you concrete constructions of three-family standard models. Then I spent some highlights about constructing abelian gate symmetries and focusing on rank 2, including studying aspects of collisions of rational sections and producing non-abelian gate symmetries in this moduli space. And the last topic was doing non-trivial aspects, namely Z3, discrete symmetry in F theory, and actually connections of non-trivial elements of Tate-Shafarevich groups and different M theory vacua, not F theory vacua. Well, there is more to do, but we would like to actually be able to determine directly torsional homology in the Jacobian fibration of the geometries with multisection, because it's also, there is a law that it's in one-to-one correspondence with the dimension of the Tate-Shafarevich group. So constructing really torsional homology of the Jacobian fibration of the multisections. And really an intriguing thing, I hope we'll make more progress, that one day I could tell you more how we understand geometrically non-abelian discrete symmetry in F theory. And that may have to do with some twisted torsional homology. But hopefully maybe in a year from now we can say something more about it. Thank you.
Questions?
So, do I understand correctly that you do have a concrete model where you have a discrete symmetry that rule out photon decay? Or
we are building that model. You see, what I have constructed really, in principle, examples that has discrete symmetry, but I haven't chosen a particular further property of vibration that will produce for me the standard model gauge group. Actually, we are working on a model that would have, you know, in one of those, using the hypersurfaces in this two-dimensional Toric examples, there are examples where there is a bisection. So there is a discrete gate symmetry directly there and the abelian gate symmetry. So that's exactly the example we want to study for the purpose of excluding, you know, by R parity both the proton decay, but we also want to get better idea about the gauge couplings. So the technicalities there have to do with dealing, constructing also fluxes, because we're dealing with chiral matter. It's not just geometry. So that's what keeps us being stuck a bit. But in principle, you know, there's conceptual thing about discrete symmetries and features, but also embedding together with standard model construction some particular toric curves. Okay.
Other questions?